Welcome to 9.4, comparison of series. So we're going to look at the direct comparison test and then the limit comparison test, just to use or more options to help prove convergence or divergence of series. So let's first look at the direct comparison test. So if we have sequences AN and BN, and AN is smaller than or equal to BN, okay? So A is smaller than B, so that's what we have to kind of keep in mind. If the series of B sub n converges, then the series of A sub n converges, all right? So that means if the larger converges, so does the smaller one. In terms of a sequence, let's just get a visualization here, all right? So here's Bn, all those points plotted. AN is the smaller sequence, so it makes sense that AN must converge, right? The limit as B sub n, the limit as n goes to infinity of Bn goes to 0, so then the limit as n goes to infinity of A sub n goes to 0. It makes sense. If the big one converges, the small one converges. So if we're now talking about series, right? If the series of B sub n converges, then so does the smaller one, A sub n, right? That makes sense, okay? Because A sub n will always be smaller. But what happens if B sub n diverges? Well, if B sub n diverges, it goes off to infinity. There's not much that can be said about A sub n. Maybe A sub n converges, or maybe A sub n also diverges, that series, okay? So this is just saying if the larger converges, so will the smaller one, okay? Now, kind of in reverse, if the series for A sub n diverges, meaning the smaller one diverges, then the bigger one will also diverge, okay? So if the smaller diverges, so does the larger one. In terms of the sequence, if A sub n diverges, well then the bigger one also has to diverge because it's always bigger. In terms of the series, okay, if A sub n, the series for A sub n diverges, it goes off to infinity, then so does the bigger one. It has to. There's nowhere else for it to go, otherwise it will turn out to be smaller. However, if the smaller one converges, then we don't know anything about B sub n. Maybe it also converges, or maybe it diverges. So really, in the grand scheme of things, we have to remember these two phrases here. If the larger converges, so does the smaller. If the smaller diverges, so does the larger, okay? So when we're comparing in these examples here, we have to think, well, which one's bigger, which one's smaller? So for instance, if we go to this first example here, okay, where we have the series of 1 over 2 plus 5 to the n. Now, if we use the nth term test, the limit would equal 0, which means the nth term test is inconclusive, right? But this portion here, this 1 over 5 to the n, it kind of looks like a geometric, right? A geometric series, but we've got this 2 plus. But what we can do is we can compare it to that geometric series, which is a converging geometric series with r equaling 1/5. So now we're just going to compare. Well, we call this A sub n, okay? So here's our AN, all right, this guy right here. And we're going to compare it to B sub n. This guy over here is our BN, okay? So when we compare those, this guy, our A sub n, is going to be smaller because it's got a bigger denominator. Okay, so this is our smaller, this is our bigger. Since the bigger one converges, it's a geometric series with r being 1/5. Since this guy converges, so does the smaller one. So by the direct comparison test to a converging geometric series, this series from n equals 1 to infinity, it also converges. And that's all we really need to do. We need to show that the sequence is either bigger or smaller than the comparison, okay? And then depending on what the comparison does, we can make our conclusion. So let's take a look at this next example. All right, so we are looking at our series of 3 over the square root of n minus 1, okay? Now, this kind of looks like a p-series, but let's compare it to an actual p-series, all right? That 3 in the numerator doesn't make a difference, but we're going to compare it to 3 over n to the 1/2, which is a diverging p-series where p is 1/2, okay? So, now we have to compare and see which one's the bigger, which one's the smaller. Okay, now a sub n is the larger one because our denominator is smaller than this denominator. Our numerators are staying the same. So, since the smaller one diverges, the larger one also has to diverge. So by direct comparison to a diverging p-series, this series has to diverge. Now, one thing to notice is now we're starting at n equals 2 versus before we were n equals 1. In the grand scheme of things, this index has no effect on convergence or divergence. So that index shift has no effect. Okay, so just something to note. All right, finally, this last example here for the comparison test, direct comparison test. If we take a look at this guy here, now we're 1 over the square root of n plus 3. So similarly to the previous example, we might think, well, let's compare it to 1 over the square root of n, which is a diverging p-series. However, which one's larger now? So this a sub n has a bigger denominator, so this one is smaller, okay? This one's smaller than what we're comparing it to. If the larger one diverges, what does that mean? Well, remember, if we look up here, okay, at this example over here, if the larger one diverges, we can't make a conclusion about the smaller one, so we need a better comparison. So this comparison, no good. It's not helping us, okay? So let's try something else where now we can compare this guy to a smaller sequence, okay? So what if we compare it to 1 over n, which is still a harmonic series which diverges, okay? And now we can compare it. Okay, so 1 over the square root of n plus 3 is going to be bigger than 1 over n when we have this index shift of n being greater than 9. So everything after n greater than 9, this holds true. Okay, so remember that index shift is not going to affect convergence or divergence. We're really looking at what's happening as n goes to infinity, right? Okay, so now since this is the larger one and we're comparing it to a smaller sequence or a smaller series that diverges, if the smaller diverges, the larger one also will diverge. So by a direct comparison to a diverging harmonic p-series, our original series will also diverge. The next comparison series is called the limit comparison test. Okay, so we had the direct comparison and now we have the limit comparison. So again, this is comparing two series, all right, both of which are positive. Okay, so what the limit comparison test says, if I take the limit as n goes to infinity of that a sub n over b sub n, those sequences, and I get some number c, where c is greater than 0, then both an and bn converge or diverge based on what we're comparing it to, and we typically compare it to b sub n. So we're going to compare it to a series that's either going to converge or diverge, and then the limit comparison test will let us make our final conclusion. So for instance, let's look at this first example here. All right. If we have our series 3n plus 1 over 4n cubed plus n squared minus 2, this is our a sub n, okay? What we're going to compare it to is ultimately we want these leading coefficients or these powers to be identical, all right? The degree in our numerator to equal the degree in our denominator. So I pick a b sub n accordingly, all right? Now remember, we're dividing by bn, which is like multiplying by the reciprocal. So if I let bn be 1 over n squared, eventually when we take the quotient of it, I'm going to be multiplying this denominator by the numerator of a sub n, okay? All right, so if we let b sub n be 1 over n squared, then this series is a converging p series where p is equal to 2. Okay, so now we're going to set up the limit comparison test, okay? So again, we're going to take the limit as n goes to infinity of an over bn. So an was 3n plus 1 over 4n cubed plus n squared minus 2. bn is 1 over n squared. So instead of dividing by a fraction, we're really multiplying by the reciprocal. And this is where I say, okay, we want to pick a b sub n so that when we do set up our limit, we're going to get the same powers in the numerator as in the denominator, at least those leading the degrees, I should say, okay? So now we can clean this up, multiply the numerator by n squared, and we get the limit as n approaches infinity of 3n cubed plus n squared over 4n cubed plus n squared minus 2. If we use direct substitution, we have infinity over infinity. So we'll have to use L'Hopital a few times. I kind of skipped that over. And we're going to be left with 3/4, okay? 3/4 is bigger than 0, okay? So this works out. So since 3/4 is bigger than 0, by the limit comparison test, so I said LCT, limit comparison test, our series converges because we are comparing it to a converging p series. So since bn converges, then since the limit comparison test gives us a value that's greater than 0, we can say our original series converges, okay? All right, let's take a look at this next example. So I want you to think about, well, what are we going to compare it to, right? So what is the degree of our denominator? The degree of our denominator is really the square root of n squared, which is just n, okay? So thinking about that. So what are we going to let bn be? Well, bn is going to be 1 over n, okay? Which is a diverging p series. When we're looking at the series of it, it's a harmonic p series, okay? So now when we're setting up our limit comparison test, we're going to take the limit as n goes to infinity of an over bn, which remember, instead of dividing by a fraction, it's multiplying by the reciprocal. And I'm just going to clean this up. So I want it all underneath the square root. So instead of 5n over the square root, we're just going to convert this. So remember, 5 times n is the same as the square root of 25n squared, okay? So I just rewrote that. So now we have one big radical, okay? When we use substitution, we get infinity over infinity. When we use L'Hopital 2 times, and we kind of simplify things, we're going to be left with the limit as n approaches infinity of the square root of 25, okay? Just the coefficient, which is 5. Which is greater than 0, okay? So, by the limit comparison test, since we are comparing this series to a diverging p series, we can also say that the original series of 5 over the square root of n squared plus 2n plus 7 also diverges because we are comparing it to a diverging series, okay? All right. Before we move on to this next example, I want you to think about what we can compare it to. So think about what bn should be. Then pause the video a second, think about bn, and then come back. Okay. So what I kind of do is some side notes every once in a while. Is I say, all right, well, what is the power of our numerator and what is the power of our denominator? Okay, so the power of our numerator, we have n to the 2/3, right? and our denominator is n squared. So what we want is when I multiply this guy by something, I want it to equal n squared. Okay, so what is that something I want it to equal? Well, we should say, well, n to the 2/3 times n to the 4/3 is going to get us n squared. So what I want bn to be is 1 over that. 1 over n to the 4/3, because when we set up our limit, dividing by a fraction is like multiplying by the reciprocal. Okay, so we're going to let bn be 1 over n to the 4/3. So we're going to compare it to that series, which is a converging p series with p being 4/3 greater than 1. So now when we set up our limit comparison test, we're going to take the limit as n goes to infinity of an over bn, which is like multiplying by the reciprocal. Okay, now if we multiply this out, okay, I can multiply the numerator because they're both underneath the cube root. So n to the 4th times n squared is n to the 6th, 4 times n to the 4th. So we have the cube root of n to the 6th plus 4n to the 4th, okay, all over our denominator, and we're taking the limit as n goes to infinity. Well, I want to clean this up so that when I use direct substitution, and I might have to use L'Hopital, I want to make our lives a little easier. So if I really just multiply the numerator and denominator by something, I can clean it up, and direct substitution will make our lives a little easier. So we can multiply both the numerator and denominator by 1 over n squared. I just rewrote this in terms of the radical, right? But this is the same as saying 1 over n squared, okay? But we just have to think about it in terms of the cube root so that we can simplify this portion a little bit more. So now we're going to multiply 1 over n to the 6th times each of these terms, and we get the cube root of 1 plus 4 over n squared, okay? And then our denominator is going to become 6 minus 1 over n minus 1 over n squared. So now when we use direct substitution, this portion is going to go to 0 along with this portion and this portion. Those guys all go to 0 as n goes to infinity. So we'll be left with the cube root of 1, which is just 1, over 6, which is greater than 0. So we can make our conclusion by the limit comparison test. This series converges because we're comparing it to a converging p series. Okay? One last note about the limit comparison test is that if the limit as n goes to infinity of an over bn is equal to plus or minus infinity, or it doesn't exist, then the limit comparison test is inconclusive and we have to use one of the other tests that we've learned so far. If you have questions, let me know.